But in the second half of the universe, for the last 7 to 8 billion years, the expansion rate of the universe has been ever increasing, so we say the universe is now dark energy dominated.
According to the Standard Model, it now represents 68% of all the energy in the universe. Dark energy plays an important role in the standard cosmological model. If our understanding of it is wrong, then so too is the model, which means the age of the universe we get from the CMB is wrong too.
Since nobody has a clue what dark energy is, there are a lot of different theories. But the biggest question of all is simply, is it constant?
Our standard assumption about dark energy is that it's pushing apart the universe with the same strength throughout the history of the universe.
Now, physicists are wondering if that idea is wrong. Maybe, in the early universe, dark energy acted differently.
Hey, you know the whole dark energy thing that's messing with the universe today? Maybe it messed with the universe back then.
It could be that dark energy really has affected the rate of expansion a lot more than we thought. This is going to throw a big monkey wrench into our idea of how old the universe is and what it was like at different eras.
The theory is called New Early Dark Energy.
So the idea behind New Early Dark Energy is that dark energy was present during the very early periods of the universe, but in a very different state. Just like you can think of water being present in two states. It can be liquid water if the environment is quite hot, or it can be frozen water if the environment is colder.
We call that a phase change. Maybe in the early universe, dark energy underwent a phase change as well. It was different before then and acts differently now.
According to the theory, this more energetic state of early dark energy pushed apart the early universe much faster than we thought.
So that speeds things up in the opening moments of our universe, which starts to actually bring things back into agreement when you look at interpreting both the cosmic microwave background and the distance ladder measurements.
One of the things that we see in the universe is that things change with time. Density changes, matter changes, energy changes. Why not dark energy?
Adding new early dark energy to the early universe changes the Standard Model. The CMB gives a higher figure for the expansion of the universe. And finally, an age that matches the one given by the distance ladder method.
If you think about that bridge analogy, where the two parts just don't meet, the early dark energy adjusts the angle of the early universe part of the bridge, and it just gets them to actually meet in the middle.
It's still controversial, but new dark energy may be detected in detailed measurements of the cosmic microwave background.
I mean, in one sense, like, oh, do we really need to overcomplicate the universe here? But you know what? The universe is under no obligation to be simple.
But there's one thing physicists can agree on.
Dark energy truly is a can of worms we've just opened, and there may be some big changes coming up.
There is a more radical possibility. Maybe we need to ditch dark energy altogether and question one of the most famous theories of all, general relativity. Is it possible? Did Einstein make a colossal mistake? In trying to work out the age of the universe, physicists have started a revolution. A revolution that could overturn everything we thought we knew about how the universe works, including the bedrock of modern physics, Einstein's theory of gravity, general relativity.
Underlying everything, all of cosmology, is general relativity. But maybe we need a completely new understanding of gravity.
Gravity is a strange force. It's always attractive. The Earth pulling on us gives us our weight. The force of gravity acts over huge distances. The Sun tugs on objects throughout the solar system. The Milky Way pulls on other galaxies.
On the one hand, gravity is incredibly familiar to us, you know, the apple falling from the tree and all of that stuff. And we also know that gravity behaves in a very predictable way throughout our solar system, from all the spacecraft and things we've sent out. But when it comes to how it behaves on incredibly tiny scales, and also on incredibly large scales covering the whole universe, it's possible that we just don't yet have the right picture of what's going on.
Einstein's model of gravity has remained largely the same for 100 years.
So much of modern physics is really standing on Einstein's shoulders. But at the same time, we can't ever take anything for granted.
Claudia de Rham works on a theory called massive gravity. It's based on a key part of Einstein's theory that says gravity doesn't have mass.
Once you understand that general relativity is the theory of a massless particle, the immediate response should be, well, what if it was massive?
The theoretical particle that carries gravity is called the graviton. If gravitons don't have any weight, then there's nothing to slow them down as they speed through the universe. They can act over infinite distances, just like photons of light.
So one galaxy on this side of the universe can actually pull on a galaxy that's right on the other side of the universe.
But if gravity has weight, things change.
In some sense, we attach a little backpack to our graviton particle. Its effect is to slowly slow it down just enough so as to make its effect on very large distances being a tiny little bit weaker. And that's a way to switch off the effect of gravity on huge cosmological distances.
If gravity is a little bit weaker, a galaxy on this side of the universe can't pull on one on the other side of the cosmos. It has a huge effect on the expansion of the universe.
If the force of gravity actually just switches off at large distances, then you no longer have to counter the fact that everything's pulling everything else together, because it isn't anymore. So that would quite naturally explain why the expansion of our universe would be speeding up.
This acceleration is what we see in the universe today. Currently, we use dark energy to explain it.
So if the graviton has mass, that means that we can get out of the universe what we see without the need for dark energy.
What if actually what we were observing is simply the first sign of gravity switching off at very large distances? Maybe we're just observing the first effect of the graviton having a mass.
Without dark energy to deal with, the universe is a lot easier to explain.
Maybe we don't need these complicated physics. Maybe it's just all the normal ingredients of the universe, but operating under a different set of rules.
Claudia hopes her theory will soon be put to the test. Around 2037, we'll have a new gravitational wave detector, the Laser Interferometer Space Antenna, or LISA. It'll be bigger than LIGO and will orbit the Earth.
When LISA get out there in space, we'll even have a bigger handle on gravitational waves evolving throughout the whole universe. And so it will allow us to go very deep in our understanding of gravity.
LISA is a system of 3 satellites arranged in a giant triangular formation, 1.5 million miles apart. It should pick up very low-frequency gravitational waves from more ancient events, perhaps even shock waves from the birth of the universe. If the graviton has mass, then the waves will arrive more slowly than predicted. But until we receive those signals, all bets are off.
It's a big deal to propose a difference in gravity, but then again, we don't know.
I'm making no bets. The universe has proven itself to be so deceptive. So I'm gonna wait until it tells me what it is.
The question of the age of the universe opens Pandora's box. And the expansion rate of the universe holds another secret. Our ultimate fate, how the universe will end. We know exactly how the Earth will end. In around 5.4 billion years, the Sun will turn into a red giant, expanding to 1,000 times its current size. The Earth will be destroyed. Humans, if we still exist, will have long deserted our home planet. But how will the universe end?